Okay, lesson 3. So yesterday we talked about the application of exponential functions in terms of finance, and we had simple interest and compound interest, and today we're going to take it on to more growth functions and decay. So an exponential function, as you will see, written yet again, can be written in any form: y equals ab to the x, where b is greater than 0 and a is not equal to 0. So a can be positive or negative. When a is positive, you're going to have, when b is bigger than 1, you're going to have a growth function, and when b is a fraction, you're going to have a decay. So we're going to talk about what those look like. It says there are many applications of exponential functions in real life. In some cases, the function y equals ab to the x can be written in disguised form. For example, a equals p times 1 plus I to the n is an exponential function whose base is that 1 plus I. So yesterday when we had the example like $2,000 being invested at 6% interest, we went 1 plus 0.06 to the n, whatever. So that became 2,000 times 1.06. See it? This 2,000 is the A, and this 1.06 is our B, and the n is like the x. So it's really very, very similar to what we've already done. So we can use variations to solve problems involving population growth, the growth of bacteria, or decay. Radioactive decay is the most common kind. All right, so in example 1, in 2012, the university population of a country was 160,000 and was increasing at an annual rate of 4.5%. So right off the bat, we need to state the values for A. A is the initial amount. Now, can I just give you a heads up on this formula? You never times A times B and then take it to the power of X. That is not following our order of operations. The X only applies to the B. We must do that first and then multiply by A. So just in case that's been a place you've made mistakes, don't ever times the A and the B together. All right, in this case, the A is 160,000. What is the B? What is the base? Well, it's increasing at an annual rate. That means there's all of it, or 100%, plus 4.5%, which is 0.045. So let me write that again. 100%, like this, plus 4.5% would be like that. And when you did that, you'd have 104.5%. Correct? So if I change the 104.5% to a decimal, I will actually get 1.045. So that's how you get the base of your exponential function. Part B says, write an equation to represent the university population, P, of the country as a function of the number of years, N, since 2012. So we're just going to say, okay, B or P is equal to 160,000. That's my initial amount, times my rate of growth to the power of however many years we're going to do this. So determine the population in the year 2015. So we're simply going to rewrite the equation, and we're going to put, notice from 2012 to 2015 is your 3 years. You're going to put that up there. And when you did the math on that, you would get 182,587. 182,587. That is the population in the year 2015. So make sure you put 1.045 to the third power first. Take that answer and times it by the 160,000. Part D says, if the population continues to grow at this rate, determine the number of years, find the number of years, that's your N, to the nearest year for the population to double. So in other words, we're going to go, our first beginning amount is 160,000. And we want that to double. So we want this to become 320. And we don't know, we know the same rate of growth, but we don't know N. And what you'll find when you want this to double is that when you divide out by the 160,000 on both sides, This is going to turn into a 2. You'll notice that happens every time. When you want it to double, you'll get a 2 on that side. Now, how do we get n? N is an exponent. The rule is every time you look for an exponent, you do the inverse operation of exponents, which is logarithms. We're going to change this to a log. Log of what base? Well, a base is always a base. So 1.045 is the base of this exponential part. So it's now the base of my logarithm. The answer to a log is always the exponent, and 2 is the argument. We take log of 1.045, that is the base. Take the log of 2 with that base, and you will get 15.747 and a few. So then it says to the nearest year. We have to go back and make sure we answer the question. So n is going to be 16 years. Okay, make sure you answer in the proper way. All right, next page. This one says the number of fish in a lake is decreasing by 5%. So right away, you're going 100%, and we're going to decrease by 5%. That's going to give me 95%, correct? So have that in your head. All right. So state the base of the exponential function. There it is. 0.95 will be the base, right from the 95%. Write an equation to represent the number of fish present after t years. Use n naught, this little n with the subscript 0, we say n naught, to represent the initial population. And n sub t, or n of t, I should say, to represent the final. So we're going to go like this. N of t, so in other words, the population with respect to time, the number of fish is going to equal my initial amount times my rate of growth for t years. So now we can answer the question, now we have an exponential. Do you see how it's the same kind of as y equals ab to the x? See how the a is the initial amount, in this case it's n naught, and b is the 0.95. So hopefully you can recognize that. Okay, if there were 2,500 present in June, how many of 2012, how many would you expect to see in 2017? So the present amount, or the initial amount, will be your 2,500, 0.95, and we want to know how many there's going to be in the end. Now, do we know how many years there are? Yes, there are 5 years. This is happening 5 times. So you throw your 5 up as the exponent. You take 0.95 to the 5 first. And when we do that times 2,500, we'll get 1,934. Make sure you put that on your calculator and get that to happen. So the 0.95 to the 5 should happen first, and then times that answer by 2,500. Now it says how many years. Right away I go, oh, that's the n part of my formula. How many? That's the part I'm not going to know. How many would it take for the population to reduce to half? So I'm starting with 2,500. I want this to be 1,250. In the end, my rate of growth, or in this case, decrease, is losing 5%. So I put 95, and I don't know how many years it takes, or n or t, whatever you're using. All right. Now anybody want to guess what's going to come out here in the front? It's going to be a half, isn't it? Because we're going to divide by 2,500 to isolate the t. We get 1/2 here. It's equal to the base to the exponent. And now, what are you looking for? Looking for the exponent. So you always do the inverse operation of exponents, which is logarithms, and you turn this into logarithm functions. So we're going to go like this over here. We're going to say the log, a base is always a base. That's the base. It equals the exponent, and we're going to put in our 1/2 over here. So we should be able to go base to the exponent equals the argument. And that's what we have here. We have a base to the exponent equals the half. Okay, you type that in your calculator, the log of 1/2 over the log of 0.95, or you use your base. So I'll just remind you again that you can type in log of 0.5 over log of 0.95 if you don't have the base function on your calculator to find what t is. And t is going to give you 13.51. And then some more. And what does it ask for? To the nearest tenth. So 13 and a half years. Okay? There you go. 13.5 years. Good. All right, last one of these examples, and then we'll go to doubling or half-life and double time. It says the intensity I naught of a light source is reduced to I after passing through d meters of fog. So in other words, when your light is shining through fog, the intensity lessens. That's why it looks dimmer up ahead, right? So it has a formula for you. I want you to be comfortable with that formula. So I naught, this little I naught is the beginning, okay, or how much you have at the start. This I is what you're going to end up with. This is the end result, just like it's always been before. Okay, so at what distance, that means I don't know d, that's going to be my question, to the nearest hundredth of a meter, will the intensity be reduced to 1/4 of its original value? So in other words, my final result is going to be 1/4 of what it was to start with. That will be the final end result. And this part is all the same. I don't actually have to do anything different but write it down. 0.12d. Now what I'm going to have is, when I divide out this I naught, it cancels just like we've been seeing before. And what you have is 1/4 equals e to the negative 0.12d. Now how, in tarnation, do you solve that? Who remembers what the inverse operation of the E function is? I'm just going to write that up there again. It looked messy. You're right. It's the natural log. So we're going to take the natural log of both sides. And when we take the natural log of both sides, it's going to look like this. We're going to have the natural log of 1/4 equaling, now what happens to the natural log and the E function? Well, they're inverses, so they cancel, or think of them as canceling, and what you end up with is negative 0.12d, and life is good. You can type in the natural log, or the ln of 1/4 on your calculator, and divide it by negative 0.12, and d is going to equal 11.552, we're going to go to the nearest hundredth, 11.55 meters. All right, let's move right along here. We've got a lot more to go. All right, so we just talked about light intensity and fish decreasing. So we know we can do that. What we're going to talk about now is more about science, which is the decay of a radioactive substance. That radiation substance decays and becomes less over time. We talk about a half-life. There's a lot of discussion in science about the half-life of this radioactive substance. That means that only half of it will remain after a certain time. So if I said there's 100, I don't know, 100 grams of a radioactive substance and it has a half-life of 5 days, that would mean in 5 days there would only be 50 grams left. And then in another 5 days there would only be 25, and it keeps going down by a half. So same thing remains, like this is exactly the same formula. So if I was to write this down, guess what A is? A is the initial amount. B is how it's changing. That's your rate of growth or decay. And in this case, we're going to have a half. And then X is how many times it happens. So it's all the same as what we've done with money, what we did with the fish, what we did with the interest. It's all the same formula. The only difference is, here it is right there, this T and this H. Because the T on the top is the time that you're given, and the H is the half-life. So if I had 50 days, for example, and we'll do some. If I said how much will there be left in 50 days? And the half-life is 5 days. That means every 5 days is going to be 1/2 as much as it was. We would put the 50 up here and the 5 down here, and we'd say, okay, it's going to get cut in half 10 times. In 50 days, if the half-life was 5 days, I'll write it down so you can see. If the half-life was 5 days, then in 50 days' time, it's going to happen 10 times. So I'll show you how that works in a little bit. Same thing for doubling. The only difference between the doubling formula is that there's twice as much as there was before. So maybe this is bacteria, and they're doubling every 10 hours. And so you have to figure out what this is going to be. And again, it's the time you're given over the time it takes to double. Okay, so we're going to show you how those work in a few examples. I think it'll make more sense. Okay, so here are the formulas. Again, A0 is the initial amount, C is what's happening, how it's changing, the tripling time, doubling time, half-life, whatever it is. T is the amount that you're given, and P will be the amount of whatever the half-life is, or the period, this says period of time for doubling, tripling, half. Okay, so let's go do an example. A patient feeling ill had a sample of bacteria taken from her throat. The sample contained 387 cells. 24 hours later, the sample was recounted and was found to contain 8,012 cells. Find the doubling period of the bacteria to the nearest tenth of an hour. So here's the things I want to know. If I just use that, this 8 is how much do we start with? 387. How much do we end up with? That's this part here in the Y, which is 8,012. What is the rate of change? Well, it's doubling. How many times is it going to double? And it says, I don't know. It says, find the doubling period. What I know is I have 24 hours. I put that on the top. I don't know how long it takes to double. So that is how you set up your equation. So the time that you're given, the total time given, like this is how much you have time has passed, goes on the top of this fraction right here. All right, we do the math that we can. So we divide by the 387. You always separate that first. And you're going to take 8,012 divided by 387, and that's going to give you, I'll get my calculator so I can figure it out. 8,012 divided by 387. It gives you, if I go over here, 20.7028. Take several decimals. This equals 2 to the power of 24 over d. All right, every time you're looking for the exponent, you take the log of it, or you move it into like logarithmic form. So I'm going to go log. The base of the base is always a base. It equals the exponent. And the argument goes here, 20.7028. So if I take the log of my answer, and then I divide that by the log of 2, because my calculator doesn't have that base, I get 4.37. So I get this to be 4.3718 equals 24 over d. And now you just need to cross multiply and divide, or however you want to do that. So I'm going to go 24 is equal to 4.3718 times d. So now I divide by that. And I get 5.5. So let's answer that 5.5 in terms of what we're talking about. This was talking about hours, 1 to the nearest tenth of an hour. So I'm going to make sure that I write on here 5.5 hours. Okay, I'll show that to you a little bit so you can see what I did. So I typed in this number into my calculator, put it here, and then I just cross-multiplied and divided to get down to my 5.5. Okay, 2 more quick questions and we're done. I'm going to erase this for you here. So I might just set this up and have you solve it, because this is taking a while, but. Okay, it says in April 1986, a nuclear accident at Chernobyl contaminated, that's in Russia, I believe, contaminated the atmosphere with quantities of radioactive iodine-131. If the half-life of radioactive iodine-131 is 8.1 days, that means in 8.1 days there will only be half as much left as there was before. Okay, so determine the number of days, the nearest day it took for the level of radiation to reduce to 2% of the original level. Okay, so what we're going to assume, because we have to assume there was 100% of the material at the beginning. And we want to know how long did it take to get to 2%. So this is the 100% initial, 2% of what we would want. What are we doing here? Well, it says it's the half-life, so that's how I'm decaying. And what I know is, I don't know what the scope of the time was. I'm going to put a T for time, but I know that it's going to be divided by 8.1. Every 8.1, it will be half as much as there was. So now I just do the math. So I divide by 100 here, divide by 100 here, I get 0.02 is equal to 1/2 to the power of, whoa, shucks. To the power of T over 8.1. Once again, looking for an exponent, you take the log. So I take the log, I change it to logarithmic form. The base is a base, it's always a base. That's my base. This is my exponent. This is my argument. Now I'm just gonna, I can find out what that number was. I'll do it here. The log of 0.02. And then I'm going to divide that by the log of 0.5. And I get 5.6439 is equal to T over 81. So now I just cross multiply. So I times that by 8.1. And I get 45.7 equals T. What does it want? Go check. Up here it says to the nearest day. So I'm going to say 46 days. That is my final answer. Okay, so it turns out you do the same process over and over and over. If you can just figure out how to set up your equation, all of this algebra at the end here, all of this taking the log and turning it into logarithmic, it's repetitive over and over and over. It's the same thing. Okay, so I'll do one more example and we'll quit. That's all we got left. It says a radioactive isotope has a half-life of 7 years. That means it takes 7 years for there to be half as much left. So this one says, okay, use the formula. I don't even use that formula. I just know what I have to determine how much of the isotope must initially be present. Ooh, I don't know how much I have initially, but I'm going to decay to 60 grams. So that's my final. I don't know how much there is. I can put A0 for the beginning. And I know that I have a half-life. Talk about half-life here. And it's going to happen in 14 years. That's the length of time I have. But what is the half-life? The half-life is 7 years. So I know it's going to happen twice. 14 over 7. So I go 60 equals A0, 1/2 to the 2. 1/2 to the 2 is a very nice number. It's 1/4. So I can divide by 1/4 on both sides. Dividing by 1/4 is the same as multiplying by 4. And so there must have been, the initial amount would have been 240 grams. So that was pretty simple. It says write an equivalent formula with C being 2. So what if I needed it to be a base of 2 and not a 1/2? So I could have written, okay, 60 equals A0. If I want that 1/2, it could be 2 to the negative 1, correct? It would be the same as a 2. Then this will be 14 over 7 is squared. So really, it could become 60 equals A0, and then this would be 2 to the negative 2. Correct? All right. I don't think I'm going to do question C. I don't think we need to know it. So I'm going to quit there. Good luck. Work hard.